Welcome to Curiosity After Dark, where we explore the mysteries of space and time while the rest of the world sleeps. From distant galaxies to frozen moons, these stories are designed to spark wonder and curiosity as you drift off to sleep. So, lie back, relax, and let the universe unfold. Water on Mars. The search for water on Mars has been one of the most enduring and transformative quests in planetary science. Once thought to be a dry and barren world, Mars is now known to have had a dynamic and watery past. Over the past 2 decades, numerous robotic missions, most notably NASA's Curiosity and Perseverance rovers, have revealed compelling evidence that liquid water once flowed across the Martian surface in rivers, lakes, and possibly even oceans. Today, although liquid water is rare on the surface due to Mars' thin atmosphere, ice has been found just beneath the surface and at the poles, indicating that water is still present and playing a role in Martian geology and climate. These discoveries have not only reshaped our understanding of Mars's history, but also intensified the search for past or present life on the red planet. Mars presents a landscape carved and shaped by the unmistakable signatures of water erosion, winding river valleys, deltas, lake beds, and sedimentary rock layers. Early observations from orbiting spacecraft like Mars Global Surveyor and Mars Odyssey hinted at such features, but it was the deployment of advanced rovers that truly revolutionized the study of Martian water. Launched in 2011, the Curiosity rover landed in Gale Crater in 2012 and began an ambitious mission to investigate whether Mars ever had conditions suitable for life. Almost immediately, Curiosity found compelling evidence of ancient riverbeds and sedimentary structures formed in the presence of standing or flowing water. One of Curiosity's major findings was the discovery of clay minerals in Martian soil. Clays form in the presence of neutral to slightly alkaline water, suggesting that at one point, Mars had environments with stable, long-term liquid water, conditions potentially favorable for microbial life. In addition, Curiosity analyzed rock samples that showed signs of ancient lakes that persisted for millions of years. These findings imply a more temperate and wetter ancient climate than the arid, freezing environment seen today. Building on Curiosity's legacy, the Perseverance rover landed in Jezero Crater in 2021. This crater was chosen specifically because orbital imaging suggested it once hosted a river delta, an ideal location for trapping and preserving organic materials. Since its arrival, Perseverance has confirmed the presence of deltaic sedimentary structures and identified rocks that were clearly altered by water. Using its advanced suite of instruments, the rover has been collecting samples that will eventually be returned to Earth by a future mission. These samples could contain biosignatures or other chemical fingerprints that reveal the past habitability of Mars. Beyond evidence of past water, missions have also confirmed the presence of water in present-day Mars, primarily in the form of ice. The Mars Reconnaissance Orbiter MRO, with its high-resolution instruments, has detected subsurface ice deposits in many regions, some just centimeters below the surface. Radar studies have shown that large volumes of ice are buried beneath the Martian regolith, especially near the poles. This ice is not only a record of Mars's climatic history, but also a valuable resource for future human exploration, potentially providing drinking water, oxygen, and fuel. Perhaps one of the most intriguing findings in recent years came in 2018, when scientists using data from the European Space Agency's Mars Express orbiter reported radar reflections consistent with a subsurface lake beneath the South Polar ice cap. Although the interpretation of these results is still debated, they raised the possibility that pockets of liquid water might still exist today beneath Mars's surface, shielded from the harsh surface conditions by insulating layers of ice and dust. If confirmed, these liquid reservoirs could represent habitable environments, isolated ecosystems where microbial life might persist. The presence of water, past and present, has profound implications for our understanding of Mars's geology, climate, and potential to support life. It suggests that Mars underwent significant climatic changes over billions of years. transitioning from a once warm and wet world to the cold desert we see today. Understanding the mechanisms behind this transformation helps scientists not only piece together Mars' history, but also draw comparisons with Earth and other planets. For instance, studying Mars' ancient hydrology may offer clues about the early Earth, where much of the geologic record has been erased by tectonics and erosion. Water on Mars also plays a central role in future exploration plans. Both NASA and other space agencies envision human missions to Mars within the next few decades. For such missions to be sustainable, astronauts will need to utilize local resources, a concept known as in situ resource utilization, ISRU. Water ice near the surface could be extracted and converted into drinking water, breathable air, and rocket fuel, drastically reducing the need to carry these supplies from Earth. Thus, locating and understanding Martian ice deposits is not just of scientific interest, but also of practical importance. In conclusion, the discovery of water on Mars has been one of the most significant developments in planetary science. Through decades of exploration, we have learned that Mars was once a blue planet with lakes, rivers, and perhaps even seas. Today, it retains vast amounts of water ice and perhaps even subsurface liquid water. These findings reshape our understanding of Mars' climatic evolution and deepen the possibility that life once existed, or may still exist, on the Red Planet. As our exploration efforts continue, water remains the key to unlocking Mars' secrets and preparing for humanity's next great leap into the cosmos. First image of a black hole 2019. On April 10, 2019, the world witnessed a historic achievement in astronomy, the first ever image of a black hole. Captured by the Event Horizon Telescope EHT, this image revealed the shadow of the supermassive black hole at the center of the galaxy Messier 87M87, located about 55 million light-years from Earth. This remarkable feat was the result of a global collaboration involving hundreds of scientists and numerous observatories working in unison. The image was not only a powerful visual confirmation of decades of theoretical predictions, but also a landmark milestone in observational astrophysics, offering humanity its first direct glimpse into one of the most mysterious and extreme objects in the universe. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape. While they cannot be seen directly, the area surrounding a black hole can be observed due to the emission of radiation from infalling matter. According to general relativity, a black hole is surrounded by an event horizon, a boundary beyond which nothing can return. Light and matter that get too close spiral inwards, heating up and emitting radiation just before crossing the event horizon. This process creates a bright ring of light known as the photon ring, encircling a dark central region where the black hole's shadow lies. Imaging a black hole, however, presents enormous challenges. The target, despite being massive, about 6.5 billion times the mass of our Sun, appears incredibly small from Earth due to its vast distance. To resolve such fine details, the ET had to achieve an angular resolution equivalent to reading a newspaper in New York from a cafe in Paris. This was made possible through a technique called Very Long Baseline Interferometry VLB-BI, which synchronizes radio telescopes across the globe to act as a single Earth-sized telescope. The EHT network included observatories in Chile, Hawaii, Spain, Mexico, the South Pole, and the continental United States. Over several nights in April 2017, these telescopes collected petabytes of radio wave data from the vicinity of M87's supermassive black hole. Because of the immense volume of data, hard drives had to be physically shipped to central processing centers at MIT and the Max Planck Institute in Germany for correlation and analysis. Teams of scientists then spent nearly 2 years developing algorithms and performing rigorous checks to reconstruct and verify the image. What emerged was a glowing orange ring with a dark central region, the silhouette of the black hole's event horizon against the backdrop of hot plasma. This image was instantly recognizable and deeply iconic, confirming predictions from Einstein's theory of general relativity with astonishing accuracy. The bright ring was not perfectly uniform, reflecting the dynamics of the accreting matter and the orientation of the black hole's spin. The success of the ET represented a powerful demonstration of theoretical physics converging with observational reality. The impact of this first image of a black hole was profound and far-reaching. Scientifically, it confirmed several key aspects of general relativity in the strong gravity regime. The shape and size of the shadow closely matched theoretical models, validating predictions about how light bends and behaves near a black hole. The observation also helped estimate the mass of M87's black hole more precisely and provided insights into the nature of accretion disks and relativistic jets, the latter of which are immense streams of particles launched from the black hole's vicinity at nearly the speed of light. Beyond the realm of science, the image captivated the global public. It was featured on front pages, in classrooms, and across social media, becoming an emblem of human curiosity and ingenuity. The project's interdisciplinary and international collaboration also served as a model for how scientific progress can transcend borders and unite people around shared goals. Dr. Katie Booman, one of the researchers behind the imaging algorithm, became a public face of the achievement, symbolizing a new generation of scientists pushing the boundaries of possibility. Following the 2019 success, the EHT collaboration has continued its work, aiming to refine the image of M87's black hole and to capture the shadow of the supermassive black hole at the center of our own galaxy, Sagittarius AS*. In 2022, the ET team released the first image of Sagittarius A*, another major milestone given the challenges posed by its smaller size and the rapidly changing dynamics of its environment. These ongoing efforts are enhancing our understanding of black hole physics, accretion mechanisms, and general relativity. The first image of a black hole is more than a stunning visual. It is a profound scientific statement. It confirmed theoretical models that had been developed over a century and proved that with enough collaboration, ingenuity, and precision, we could observe the most extreme phenomena in the universe. It opened new avenues for research, allowing astronomers to test gravitational theories in the most intense environments, investigate how black holes grow and evolve, and explore their role in shaping galaxies. In summary, the 2019 image of the black hole in M87 marked a defining moment in the history of science. It represented a triumph of technology, theory, and international cooperation. This singular image, so distant, so dark, and yet so brilliantly illuminated, offered a window into the fundamental nature of space, time, and gravity. As the Event Horizon Telescope continues to probe the universe's darkest corners, it reminds us of our ability to reach beyond the limits of our senses, using ingenuity and collaboration to bring the invisible into view. Pluto's Geology and Atmosphere, 2015. When NASA's New Horizons spacecraft performed its historic flyby of Pluto on July 14, 2015, it transformed a tiny point of light in the night sky into a richly detailed and dynamic world. Until then, Pluto was largely an enigma, classified as a dwarf planet and relegated to the icy outskirts of the solar system in the Kuiper Belt. Scientists expected a cold, geologically dead object, its surface perhaps battered by craters and unchanged for billions of years. What New Horizons revealed instead was astonishing. A geologically active world marked by vast glaciers, towering mountain ranges, smooth plains, and an unexpectedly complex atmosphere. This flyby redefined not only Pluto but also our understanding of the diversity and potential of small bodies in the outer solar system. Before New Horizons, Pluto had only been glimpsed as a blurry object through telescopes. Discovered in 1930 by Clyde Tombaugh, Pluto became the 9th planet in the solar system before being reclassified as a dwarf planet in 2006. Despite its demotion, Pluto remained of immense scientific interest due to its status as one of the largest known Kuiper Belt objects. The Kuiper Belt is a region of icy bodies beyond Neptune, believed to be remnants from the formation of the solar system. By studying Pluto, scientists hope to gain insights into this distant primordial region. New Horizons' brief but groundbreaking flyby exceeded all expectations. Traveling at over 50,000 kilometers per hour, the spacecraft passed within 12,500 kilometers of Pluto's surface, capturing detailed images and data that continue to be analyzed years later. One of the most stunning discoveries was the variety and youthfulness of Pluto's surface features, suggesting ongoing geological activity. The most iconic region revealed was Sputnik Planitia, a vast, heart-shaped plain of nitrogen ice that dominates Pluto's western hemisphere. Far from being static, this plain shows signs of convection, where heat from Pluto's interior may be driving the slow overturning of ice, crisscrossed by polygonal patterns and free of impact craters in many places. Sputnik Planitia is estimated to be less than 10 million years old, very young in geological terms. This challenges the notion that small distant worlds like Pluto are frozen in time, indicating instead that internal heat and resurfacing processes are at play. Surrounding this icy plain are towering mountain ranges composed not of rock, but of water ice, the only material rigid enough to support such elevations in Pluto's frigid environment. Some peaks rise as high as 3,500 meters, rivaling the Rocky Mountains. These features speak to the structural complexity of Pluto's crust and suggest tectonic activity driven by internal processes. The presence of possible cryovolcanoes, such as Wright Mons and Picard Mons, further supports the idea that Pluto may have experienced, or may still be experiencing, volcanic activity involving the eruption of water, ammonia, or other icy materials. Equally surprising was Pluto's atmosphere. Long thought to be a tenuous envelope of nitrogen, New Horizons found it to be more complex than expected. The spacecraft detected multiple haze layers extending up to 160 kilometers above the surface, composed of hydrocarbons formed by the breakdown of methane in sunlight. These haze particles contribute to the planet's reddish hue and play a role in surface chemistry. Although Pluto's atmosphere is extremely thin, about 100,000 times less dense than Earth's, it displays seasonal variation and interacts dynamically with the solar wind. Observations suggest that Pluto may be slowly losing its atmosphere to space, particularly as it moves farther from the Sun in its elliptical orbit. The implications of these discoveries extend beyond Pluto itself. They challenge long-standing assumptions that small, icy worlds far from the Sun are geologically dead. Instead, Pluto is a testament to the diversity and dynamism possible even in the most remote corners of the solar system. Its internal heat may be sustained by radioactive decay, and its surface and atmosphere are shaped by ongoing physical and chemical processes. These findings have prompted scientists to reconsider what constitutes geological activity and planetary complexity. New Horizons also discovered several intriguing features on Pluto's largest moon, Charon. Though less active than Pluto, Charon shows signs of a violent past, including a massive chasm system longer than the Grand Canyon and a reddish cap at its north pole, possibly formed by atmospheric material escaping from Pluto and settling on Charon's surface. The binary relationship between Pluto and Charon, unique among known planetary systems, offers valuable insights into tidal interactions and the evolution of close satellite systems. Moreover, the success of New Horizons has inspired renewed interest in returning to Pluto for a more extended mission. Scientists are now advocating for an orbiter that could study Pluto over time, map its surface in greater detail, monitor atmospheric changes, and explore its moons. Such a mission would further illuminate the processes shaping Pluto and help contextualize it among other Kuiper Belt objects. In a broader sense, Pluto's revelations have sparked a re-evaluation of planetary science. The sharp boundary once drawn between planets and other solar system bodies has become increasingly blurred. Worlds like Pluto demonstrate that geological complexity is not confined to Earth-sized planets or large moons. Even small, distant, icy bodies can be dynamic, active, and surprisingly Earth-like in some of their features. This has significant implications for astrobiology, as it broadens the range of environments that may harbor the conditions necessary for life. In conclusion, the New Horizons mission fundamentally altered our view of Pluto. What was once considered a static, icy relic turned out to be a geologically vibrant world with towering mountains, glacial plains, a layered atmosphere, and potential cryovolcanism. These findings challenge assumptions about the limitations of planetary activity and extend our understanding of what's possible in the outer solar system. Pluto's rich and complex nature reaffirms the importance of exploration and the value of venturing into the unknown. As we continue to explore, Pluto reminds us that even the smallest worlds can yield the biggest surprises. Accelerating expansion confirmed. Unveiling the cosmic mystery of dark energy. The universe is vast, ancient, and dynamic, governed by forces and phenomena that challenge human comprehension. Among the most profound discoveries in modern cosmology is the realization that the universe is not only expanding but doing so at an accelerating rate. This startling revelation, rooted in observations from the late 1990s, gained significant confirmation through 21st century missions such as the Wilkinson Microwave Anisotropy Probe WMAP and the Planck satellite. These groundbreaking projects not only affirmed the existence of an accelerating universe, but also introduced dark energy as a fundamental yet mysterious component shaping cosmic destiny. The confirmation of accelerating expansion has revolutionized our understanding of the cosmos and continues to be a central focus in space exploration and theoretical physics. In the late 1990s, two independent teams of astronomers studying Type Ia supernovae made a surprising observation. Distant supernovae appeared dimmer than expected. These observations suggested that the universe's expansion was speeding up, not slowing down as previously assumed. The results were unexpected because conventional wisdom held that the gravitational pull of matter should gradually decelerate cosmic expansion over time. Instead, something unseen, later termed dark energy, appeared to be driving the universe apart at an increasing rate. Following the initial discovery, cosmologists needed precise measurements to verify and understand this phenomenon. This is where missions like WMAP launched in 2001 and Planck launched in 2009 by the European Space Agency played a critical role. WMAP provided a detailed map of the cosmic microwave background CMB radiation, the afterglow of the Big Bang. This radiation holds clues about the early universe's conditions and structure. By analyzing the minute temperature fluctuations in the CMB, WMAP helped determine the composition of the universe: about 4.6% ordinary matter, 24% dark matter, and a staggering 71.4% dark energy. These results not only confirmed the presence of dark energy, but also indicated that it is the dominant force affecting the large-scale structure and fate of the cosmos. The Planck mission took this even further by measuring the CMB with unprecedented precision. Planck's data refined estimates of the universe's age, geometry, and composition, further corroborating the accelerating expansion and the role of dark energy. The agreement between Planck's findings and those from supernova studies and large-scale galaxy surveys added confidence to the new cosmological model. Despite these confirmations, dark energy remains one of the most mysterious components in physics. It does not interact with light or matter in any direct way that we can currently detect, making it invisible and elusive. However, its effects are observable on cosmic scales. The most accepted explanation is that dark energy is a property of space itself. According to Einstein's general relativity, space can possess energy, and this energy can exert a repulsive force. This concept is linked to the cosmological constant lambda, which Einstein originally introduced and later dismissed as a mathematical fix. Ironically, the cosmological constant has now returned to the forefront as a leading explanation for dark energy. Alternative theories propose that dark energy might vary over time and space, or that it could arise from previously unknown fields or dimensions. Some theories even suggest that our understanding of gravity may need to be revised on cosmic scales. Regardless of the explanation, the presence of dark energy challenges physicists to explore beyond the standard model of particle physics and general relativity. The confirmation of accelerating expansion has profound implications for the ultimate fate of the universe. In a decelerating universe dominated by matter, gravity would eventually slow expansion, possibly leading to a big crunch. However, in a universe dominated by dark energy, the expansion could continue forever, leading to a big freeze, where galaxies drift apart, stars burn out, and the cosmos becomes dark and cold. Some speculative models predict even more extreme scenarios, such as the Big Rip, where dark energy's repulsive force grows stronger over time, eventually tearing apart galaxies, stars, planets, and even atoms. While these possibilities remain theoretical, they underscore how dark energy fundamentally alters our vision of cosmic evolution. Space exploration has been essential in uncovering and understanding the accelerating expansion of the universe. Instruments placed in orbit, such as WMAP, Planck, and the Hubble Space Telescope, provided data unobstructed by Earth's atmosphere. These missions allowed scientists to peer deeper into space and further back in time than ever before, detecting subtle signals and patterns that ground-based telescopes cannot. Future missions promise to deepen our understanding even further. NASA's Nancy Grace Roman Space Telescope and the Euclid mission by ESA aim to study dark energy by observing the large-scale structure of the universe and mapping billions of galaxies across cosmic history. These missions will provide critical insights into the nature of dark energy, the formation of galaxies, and the geometry of the universe. In addition to observational missions, experimental physics initiatives such as the Dark Energy Survey DS and the Vera C. Rubin Observatory aim to uncover clues about how dark energy has influenced cosmic expansion over billions of years. The confirmation of the universe's accelerating expansion marks a new era in cosmology. It represents a shift from a matter-dominated view of the universe to one where dark energy plays the leading role. This paradigm shift echoes past scientific revolutions, like the acceptance of heliocentrism or the development of quantum mechanics. Understanding dark energy is now one of the most pressing challenges in physics. It forces us to reconsider fundamental assumptions about space, time, and the laws that govern them. It also highlights the interconnectedness of cosmology, astrophysics, and particle physics, as the solution may lie at their intersection. The confirmation of the universe's accelerating expansion from the 2000s to the present, catalyzed by missions like WMAP and Planck, stands as one of the greatest achievements in modern science. It has reshaped our understanding of the cosmos, placing dark energy, a force we do not yet fully understand, at the center of cosmic evolution. While this discovery opens up profound new questions, it also exemplifies the power of space exploration and human curiosity. As we continue to probe the depths of space, we may one day unravel the true nature of dark energy, unlocking secrets that will redefine not only our understanding of the universe, but the very fabric of reality itself. Precision mapping of the cosmic microwave background, unlocking the secrets of the universe. The quest to understand the origins and structure of the universe has led scientists to study some of the most ancient signals ever detected, faint echoes from the infancy of the cosmos. Among these, the Cosmic Microwave Background CMB stands as a crucial piece of evidence, offering a snapshot of the universe just 380,000 years after the Big Bang. Thanks to advanced space missions such as the Wilkinson Microwave Anisotropy Probe BUMAP and the Planck satellite, scientists have been able to create precise maps of this primordial radiation. These maps have transformed cosmology by refining our understanding of the universe's age, shape, and composition, laying the foundation for the current standard model of cosmology. The CMB is a faint glow of microwave radiation that fills the universe. It is the residual heat left over from the Big Bang, cooled over billions of years to just 2.7 Kelvin, a few degrees above absolute zero. Initially discovered in 1965 by Arno Penzias and Robert Wilson, the CMB provided the first direct observational evidence for the Big Bang theory. However, the CMB is not perfectly uniform. It contains tiny temperature fluctuations, anisotropies, that reveal the distribution of matter and energy in the early universe. These irregularities eventually gave rise to the large-scale structures we see today, such as galaxies and galaxy clusters. Mapping these fluctuations in detail allows scientists to test theories of the universe's origin, composition, and ultimate fate. Launched by NASA in 2001, the Wilkinson Microwave Anisotropy Probe BUMA was designed to measure temperature differences in the CMB across the sky with much greater resolution and sensitivity than its predecessor, the COBE satellite. Over 9 years, WMAP created an incredibly detailed map of the CMB. It provided several groundbreaking measurements that revolutionized cosmology. Age of the universe. WMAP-B determined the universe is approximately 13.77 billion years old, with a very small margin of error. Geometry of the universe. Data from BUMAP showed that the universe is flat, meaning that the rules of Euclidean geometry apply on large scales, and that the total energy density is very close to the critical density. Composition of the universe. WMAP confirmed the universe consists of about 4.6% ordinary matter, 24% dark matter, and 71.4% dark energy. These measurements help solidify the UACDM lambda cold dark matter model, which is now the standard model of cosmology. WMAP also provided insights into the rate of expansion Hubble constant, the curvature of space, and the nature of the inflationary period shortly after the Big Bang. While WMAP was a major leap forward, the European Space Agency's Planck satellite, launched in 2009, provided an even more detailed view of the CMB. Planck operated until 2013, collecting data with higher sensitivity and resolution than any mission before it. Planck's improvements included higher angular resolution. Planck could detect finer details in the temperature fluctuations of the CMB, allowing scientists to study smaller scale structures. Full sky coverage. Like WMAP, Planck scanned the entire sky, but did so with improved sensitivity. Polarization measurements. Planck also measured the polarization of the CMB, tiny patterns in the direction of light waves, which offered new insights into the early universe's conditions and the process of reionization. The results from Planck further refined key cosmological parameters. Age of the universe. Planck adjusted the age estimate slightly to 13.8 billion years. Hubble constant. Planck's data suggested a lower value for the universe's rate of expansion than previous observations, sparking ongoing debates and studies into the so-called Hubble tension. Composition confirmation. Planck confirmed WMAP's breakdown of the universe's composition with even greater precision, further validating the MACDM model. Mapping the CMB with such precision has had transformative effects on our understanding of the cosmos. These missions provided answers to long-standing questions and opened the door to new lines of inquiry. Testing the Big Bang theory. The observed uniformity and slight anisotropies in the CMB perfectly align with predictions from the Big Bang model, strengthening it as the dominant cosmological theory. Understanding cosmic inflation. Variations in the CMB temperature support the idea that the universe underwent a rapid exponential expansion-inflation moments after the Big Bang. This inflationary period smoothed out the universe while leaving subtle imprints in the CMB. Constraining the universe's shape. By measuring the size of fluctuations in the CMB, scientists could deduce the universe's geometry. Both WMAP and Planck confirmed the universe is flat with high accuracy. Refining cosmological models. These missions provided data essential for developing accurate simulations of cosmic evolution. from the Big Bang to the formation of galaxies and large-scale structures. Informing future missions, the legacy of WAP and Planck influences current and future space observatories, such as the James Webb Space Telescope, Euclid, and CMB-S4, all of which aim to explore the universe's origins and composition in greater depth. Despite their success, WMAP and Planck also highlighted areas of tension in cosmology. One of the most prominent is the Hubble tension, a discrepancy between the universe's expansion rate as measured from CMB data and that derived from observations of nearby supernovae and galaxies. This tension has prompted speculation that our current cosmological model might be incomplete or that new physics may be required. Additionally, while the CMB data strongly supports the presence of dark matter and dark energy, it tells us little about their true nature. These components, which make up 95% of the universe, remain largely mysterious. Their effects are seen in the CMB and galaxy formations, but their composition and mechanisms are still unknown. The precision mapping of the cosmic microwave background by WMAP and Planck stands as one of the most significant achievements in the history of space science. These missions not only confirmed the predictions of the Big Bang theory, but also provided a detailed blueprint of the universe's structure and history. They refined critical cosmological parameters, confirmed the universe's flatness, and established the foundational understanding of its composition. Beyond their immediate findings, these missions have ignited new scientific inquiries, exposed unexpected tensions, and laid the groundwork for future explorations. In mapping the ancient light of the universe, WMAP and Planck helped humanity peer into the cosmos's past, and perhaps even glimpse its future. As technology advances and new missions are launched, we can expect even more detailed insights into the universe's earliest moments, inching ever closer to answering some of the deepest questions in science. Where did we come from? What is the universe made of? And what lies ahead? Dark matter mapping. One of the most profound mysteries in modern astrophysics is the existence of dark matter, an invisible substance that neither emits nor absorbs light, yet exerts a significant gravitational influence on the visible universe. Although it cannot be seen directly, dark matter is thought to constitute about 27% of the universe's total mass energy content, vastly outweighing the ordinary matter we can observe. Over the past few decades, astronomers and physicists have developed sophisticated methods to detect and map dark matter indirectly, primarily through its gravitational effects on light and matter. Among these, gravitational lensing and large-scale surveys, such as the Dark Energy Survey DS and the European Space Agency's Euclid mission, have played critical roles. These efforts have not only revealed the intricate distribution of dark matter across the cosmos, but have also confirmed its central importance in the formation and evolution of galaxies. Gravitational lensing, a phenomenon predicted by Einstein's theory of general relativity, has become one of the most powerful tools for mapping dark matter. According to general relativity, massive objects like galaxy clusters warp the fabric of space-time, bending the path of light that passes nearby. When light from distant galaxies travels through such warped regions, it appears distorted, a phenomenon known as weak gravitational lensing. By analyzing these distortions across large portions of the sky, astronomers can reconstruct the mass distribution causing the lensing, including both visible and dark matter. This technique has allowed researchers to create detailed maps of dark matter over vast cosmic scales. The Dark Energy Survey, launched in 2013, has been one of the most influential projects in this field. Utilizing a state-of-the-art camera mounted on the Blanco telescope in Chile, DS observed over 300 million galaxies and mapped hundreds of millions of square degrees of the sky. A key achievement of DS has been its ability to detect the subtle gravitational lensing effects of dark matter and translate those into high-resolution maps showing where dark matter is most densely concentrated. These maps have confirmed that dark matter forms a cosmic web-like structure with vast filaments connecting clusters of galaxies and enormous voids in between. Such findings are consistent with predictions from simulations of the early universe, which suggested that dark matter acts as a gravitational scaffold upon which ordinary matter accumulates and forms galaxies. Another landmark in dark matter research is the European Space Agency's Euclid mission, launched in 2023. Euclid is designed to survey billions of galaxies over a third of the sky and to measure the geometry of the universe with unprecedented precision. One of Euclid's primary goals is to map the distribution of dark matter through both weak gravitational lensing and galaxy clustering. By studying how galaxies are distributed relative to one another and how their light is bent as it travels through space, Euclid will generate a three-dimensional map of the universe's dark matter structure. This will allow scientists to better understand how dark matter has influenced cosmic evolution over time and how it interacts with dark energy, the other major unknown component of the universe. The data from DS and Euclid, along with other surveys like the Canada-France-Hawaii Telescope Lensing Survey and the upcoming Vera C. Rubin Observatory's Legacy Survey of Space and Time LSST, collectively paint a consistent picture. Dark matter is not uniformly spread throughout space, rather, it clusters in regions of high gravitational potential. These dense areas serve as the birthplaces of galaxies and galaxy clusters. Without dark matter's gravitational influence, it is unlikely that the early universe's small density fluctuations would have grown into the large-scale structures we observe today. This central role of dark matter in galaxy formation is now a foundational aspect of cosmology. Despite these advances, the true nature of dark matter remains elusive. While its gravitational effects are undeniable, scientists have yet to detect dark matter particles directly. Several hypotheses exist, ranging from weakly interacting massive particles WIMPs to axions and sterile neutrinos, but none have been confirmed. Large-scale mapping projects, however, continue to provide valuable constraints that help narrow the field of possible explanations. For instance, observations show that dark matter interacts very little, if at all, with itself or with ordinary matter, except through gravity. This lack of interaction supports the idea that dark matter is made of particles that are fundamentally different from those in the standard model of particle physics. Importantly, the study of dark matter is not just a quest to fill in a gap in our cosmic inventory. Understanding dark matter has implications for a wide range of scientific fields, from particle physics to astrophysics to the philosophy of science. Mapping its distribution helps scientists understand not only how galaxies and large-scale structures form, but also how the universe has evolved over billions of years. It also serves as a critical test for alternative theories of gravity, such as modified Newtonian dynamics (MOND), which attempt to explain cosmic phenomena without invoking dark matter. The accuracy and consistency of dark matter maps have increasingly disfavored these alternatives, bolstering the case for dark matter's existence. In conclusion, the mapping of dark matter through gravitational lensing and wide-field surveys like DS and Euclid has dramatically advanced our understanding of the universe's invisible framework. These efforts have confirmed that dark matter plays a fundamental role in shaping cosmic structure and driving galaxy formation. While we still do not know what dark matter is made of, its gravitational footprint is clear and immense, guiding the evolution of the cosmos from its earliest moments to the present day. As future missions continue to refine our view of this hidden component, we move closer to unveiling one of the universe's deepest secrets. First direct detection of gravitational waves, 2015. On September 14, 2015, scientists achieved one of the most monumental breakthroughs in physics and astronomy, the first direct detection of gravitational waves. This historic event confirmed a prediction made by Albert Einstein a century earlier in his general theory of relativity. Using the Laser Interferometer Gravitational Wave Observatory LIGO, researchers observed ripples in the fabric of spacetime produced by the collision and merger of two black holes over 1 billion light-years away. The detection not only validated a key element of Einstein's theory, but also opened a new era in observational astronomy, allowing scientists to study the universe in a fundamentally different way through gravitational wave astronomy. Gravitational waves are distortions in spacetime caused by the acceleration of massive objects, such as neutron stars and black holes. These waves propagate outward from their source at the speed of light, stretching and squeezing space as they pass. Although Einstein's equations predicted the existence of gravitational waves in 1916, they were long considered too faint to detect with available technology. It wasn't until the 21st century that instrumentation became sensitive enough to observe these elusive signals directly. LIGO, a collaborative project involving thousands of scientists from around the world, consists of 2 facilities located in Hanford, Washington and Livingston, Louisiana. Each observatory uses laser interferometry to detect incredibly small changes in distance, thousands of times smaller than a proton's diameter, caused by passing gravitational waves. By comparing signals from both locations, LIGO can distinguish genuine cosmic events from local noise or disturbances. The 2015 detection, named GW150914, was the result of the merger of 2 black holes with masses approximately 29 and 36 times that of the Sun. As the black holes spiraled inward and collided, they released an enormous amount of energy in the form of gravitational waves, more than was emitted as light by all the stars in the observable universe during that brief moment. The signal was unmistakable, a characteristic chirp that matched theoretical predictions for black hole mergers almost exactly. This direct detection confirmed that black holes not only exist, but can merge and produce observable gravitational waves, providing a new way to explore the cosmos. The announcement of the discovery on February 11, 2016, was met with worldwide acclaim. It was hailed as a triumph of both theoretical and experimental physics. The detection not only confirmed Einstein's prediction, but also validated the existence of a previously unobserved class of astrophysical systems, binary black holes. Until that point, evidence for such systems was indirect, inferred from the motion of stars or X-ray emissions. GW150914 provided irrefutable proof that black holes could form binaries and merge in a spectacular cosmic event. Gravitational wave detection marks the beginning of a new field, gravitational wave astronomy. Unlike traditional astronomy, which relies on electromagnetic radiation, visible light, radio waves, X-rays, etc., gravitational wave astronomy allows scientists to observe events that are otherwise invisible. Black hole mergers, for instance, emit little to no light, making them nearly impossible to study with telescopes. Gravitational waves, however, carry information directly from these cataclysmic events, offering a unique and complementary perspective on the universe. Following GW150914, LIGO has detected dozens of other gravitational wave events, including more black hole mergers and, most notably in 2017, the merger of 2 neutron stars. This event, GW170817, was detected by both LIGO and the Virgo detector in Europe and was accompanied by electromagnetic signals observed by dozens of telescopes around the world. It marked the first time that a cosmic event was observed through both gravitational waves and traditional light-based astronomy, ushering in an era of multi-messenger astronomy. The neutron star collision also provided critical insights into the origin of heavy elements like gold and platinum, which are forged in such extreme environments. The success of gravitational wave detection has spurred plans for even more advanced observatories. LIGO has since been upgraded to improve its sensitivity, and new detectors like KAGI in Japan and LIGO in India are under development. The European Space Agency also plans to launch LISA Laser Interferometer Space Antenna, a space-based gravitational wave observatory, in the 2030s. These instruments will allow scientists to detect waves from sources even more distant and diverse, including supermassive black hole mergers and signals from the early universe. The implications of gravitational wave astronomy extend far beyond the detection of black holes and neutron stars. By studying how these waves propagate through the universe, researchers can test the nature of gravity itself, probe the properties of space-time, and search for deviations from general relativity. Gravitational waves might also offer clues about phenomena such as cosmic inflation, dark matter, and the structure of space and time on the smallest scales. In many ways, the first detection of gravitational waves in 2015 can be compared to Galileo's first use of the telescope. It opened a new observational window on the universe. Just as telescopes revolutionized our understanding of celestial objects, gravitational wave detectors are revolutionizing our understanding of the most violent and energetic events in the cosmos. This new capability not only confirms long-standing theoretical predictions, but also challenges scientists to develop new models and methods to interpret the rich information carried by gravitational waves. In conclusion, the first direct detection of gravitational waves by LIGO in 2015 was a watershed moment in science. It confirmed a key prediction of Einstein's general relativity, provided direct evidence of merging black holes, and launched the field of gravitational wave astronomy. This achievement stands as a testament to decades of international collaboration, technological innovation, and scientific curiosity. As new observatories come online and detection techniques improve, gravitational wave astronomy promises to reveal even more about the hidden dynamics of our universe, deepening our understanding of its origins, structure, and ultimate fate. Discovery of the accelerated inflation of the early universe. The story of our universe begins not with a quiet unfolding, but with an extraordinary burst. A moment of almost inconceivable speed and scale known as cosmic inflation. This theory, proposed in the early 1980s, posits that the universe underwent an exponential expansion in the first tiny fraction of a second after the Big Bang, growing from subatomic scales to astronomical dimensions in less than 3,210 circumflex minus 32 seconds. Over the past few decades, an accumulation of precise observational data has strongly supported this theory, suggesting that cosmic inflation not only occurred but fundamentally shaped the large-scale structure and geometry of the universe we see today. Cosmic inflation was introduced as a solution to several long-standing puzzles in the standard Big Bang model. Among these are the horizon problem, the flatness problem, and the monopole problem. The horizon problem asks why regions of the universe that are vastly separated in space have nearly identical temperatures and properties, despite not having had enough time to exchange information or energy. The flatness problem involves the fine-tuning required for the universe's geometry to be so close to perfectly flat. Inflation answers both by suggesting that the entire observable universe originated from a minuscule causally connected patch of space that expanded so rapidly it now encompasses everything we see. The monopole problem, which concerns the absence of heavy magnetic monopoles predicted by some particle physics theories, is resolved by inflation diluting any such particles to undetectable levels. The first compelling support for inflation came from measurements of the cosmic microwave background CMB, the afterglow of the Big Bang. Satellites such as the Wilkinson Microwave Anisotropy Probe Plant Observatory provided exquisitely detailed maps of the tiny temperature fluctuations in the CMB. These fluctuations are believed to originate from quantum variations in the energy density of the early universe, which were stretched to cosmic scales by inflation. The statistical properties of these fluctuations, especially their near-scale invariance and Gaussian nature, match predictions made by inflationary models with impressive precision. Planck's data, in particular, offered strong support for inflation by confirming that the universe is spatially flat and homogeneous on large scales, while also containing the small seed fluctuations required for galaxies and clusters to form. These observations have helped to narrow down the range of viable inflationary models, disfavoring some while supporting others, especially those involving a single scalar field known as the inflaton, which drives the rapid expansion. In addition to temperature data, polarization measurements of the CMB have provided further evidence for inflation. The twisting patterns of polarization known as B modes could, in theory, contain signatures of primordial gravitational waves, ripples in spacetime generated by inflation itself. In 2014, the BIC EP2 experiment claimed to have detected such a signal, but subsequent analysis showed that the result was largely contaminated by galactic dust. While definitive detection of inflationary gravitational waves remains elusive, the continued refinement of instruments and techniques keeps the possibility alive, and their discovery would be considered a smoking gun for inflation. Another line of indirect evidence for inflation comes from the large-scale structure of the universe. Surveys of galaxies and quasars, such as those conducted by the Sloan Digital Sky Survey (SDSS), show a distribution of matter that aligns with the predictions of inflationary cosmology. The way galaxies are clustered and the slight acoustic oscillations in their distribution, called baryon acoustic oscillations, mirror the early universe's fluctuations as mapped in the CMB. This consistency across entirely different cosmic eras strengthens the case for inflation as the correct description of the universe's earliest moments. The theory of inflation has also dovetailed with developments in high-energy physics and string theory, inspiring models that attempt to unify inflation with fundamental particle interactions. Some of these propose that inflation could be a generic feature of string theory's extra-dimensional landscape, potentially connecting cosmology with quantum gravity. While these ideas remain theoretical, they highlight how inflation has become a central piece in the broader quest to understand the universe's origin and ultimate fate. Despite the wealth of supporting data, cosmic inflation is not without its critics or open questions. One such question concerns the mechanism that ended inflation: how the universe transitioned from the rapid expansion phase to the hot, dense state of the traditional Big Bang. This process, known as reheating, is still poorly understood and remains an active area of research. Furthermore, some models of inflation predict a multiverse, where different regions of space undergo different inflationary dynamics, leading to separate universes with distinct physical laws. While intriguing, these ideas challenge the boundaries of testable science and invite philosophical debate about the nature of scientific evidence and falsifiability. Still, the overarching success of inflation in explaining so many features of the observable universe has made it a cornerstone of modern cosmology. It has elegantly resolved fundamental issues with the Big Bang model and connected quantum physics with the macroscopic evolution of the cosmos. Future missions, such as the Cosmic Microwave Background Stage 4C MBS-4 project and the LightBard satellite, aim to detect the inflationary gravitational wave signal with far greater sensitivity. If found, such a discovery would further cement inflation's place in our cosmic origin story. In conclusion, the discovery and continuing observational support for the accelerated inflation of the early universe represent one of the most transformative advances in cosmology. Through precise measurements of the cosmic microwave background, large-scale structure, and galaxy distribution, scientists have pieced together a compelling narrative of how the universe expanded at a breakneck pace in its first moments. While questions remain about the exact mechanism and implications of inflation, its ability to explain the structure, shape, and uniformity of the cosmos makes it a pillar of our current understanding. As technology improves and our gaze deepens into the cosmic past, inflation may yet yield further secrets about the universe's birth and the forces that shaped its magnificent unfolding. Titan's methane lakes. Saturn's largest moon, Titan, is one of the most intriguing and Earth-like bodies in the solar system, despite its alien chemistry and frigid conditions. Thanks to NASA's Cassini mission, which explored the Saturnian system from 2004 to 2017, scientists discovered that Titan is the only world beyond Earth known to have stable liquids on its surface. But instead of water, Titan's lakes and rivers are filled with liquid methane and ethane. This groundbreaking revelation not only reshaped our understanding of Titan, but also opened new possibilities in the search for life and the study of planetary processes in extreme environments. Titan had long fascinated astronomers. With a diameter of about 5,150 kilometers, it's larger than the planet Mercury and possesses a dense atmosphere, an unusual feature among moons. Its thick orange haze, rich in nitrogen and methane, obscures the surface from view, but radar and infrared instruments aboard the Cassini spacecraft penetrated this veil to reveal a remarkably dynamic world. The surface showed signs of vast, dark plains, highlands, and, most strikingly, regions that strongly resembled river channels and lake basins. The first unambiguous evidence of surface liquids came in 2007, when Cassini's radar imaged large, smooth, dark regions near Titan's poles, exactly the kind of radar signature expected from lakes or seas. Subsequent flybys confirmed these features as bodies of liquid methane and ethane concentrated primarily around the North Pole. The largest, Kraken Mare, stretches over 1,000 kilometers across, comparable in size to the Caspian Sea. Dozens of smaller lakes and interconnected river systems were also identified, forming a complete hydrological cycle of methane on Titan, remarkably similar in function to Earth's water cycle. Like water on Earth, methane on Titan evaporates, forms clouds, precipitates as rain, and flows across the surface, carving valleys and filling lakes. Cassini observed seasonal changes in cloud cover and rainfall, suggesting an active methane-based climate system. In fact, Cassini's infrared instruments captured scenes of methane rainstorms and their aftermath, darkened regions where rain had recently soaked the ground. Titan's lakes are mostly concentrated in the polar regions, with the North Pole hosting the majority of the large seas. Some lakes have steep rims and sharply defined shorelines, suggesting they might be formed through processes similar to karst lakes on Earth, where subsurface dissolution creates basins. Others are thought to be the result of cryovolcanic or tectonic processes. Some lakes are permanent, while others appear and disappear, hinting at seasonal or climatic fluctuations in Titan's hydrology. The composition of these lakes was analyzed using Cassini's spectrometers, revealing that they are mostly methane and ethane, with traces of dissolved nitrogen. The presence of these hydrocarbons in liquid form is only possible because of Titan's extremely cold temperatures, averaging around -179 degrees Celsius. Despite this frigid environment, Titan shows an Earth-like level of geological and meteorological complexity, something few scientists expected from an icy moon. Titan's methane lakes are not just a scientific curiosity, they hold profound implications for the study of planetary systems and astrobiology. The presence of stable surface liquids, an active climate system, and a thick atmosphere make Titan a unique laboratory for studying prebiotic chemistry and the potential for life in environments radically different from Earth. Some researchers even speculate that exotic life forms, based on liquid methane rather than water, could theoretically exist in Titan's lakes, though this remains highly speculative. Even in the absence of life, Titan offers invaluable insight into how complex chemical processes operate under conditions vastly different from those on Earth. Its thick atmosphere, dominated by nitrogen and methane, undergoes continuous photochemical reactions driven by sunlight and Saturn's magnetospheric radiation. These reactions create a haze of organic molecules that settle onto the surface and may interact with the lakes, creating complex organic compounds, possibly similar to those that preceded life on early Earth. Titan's allure has only grown since Cassini's mission ended in 2017. NASA is currently preparing the Dragonfly mission, set to launch in the mid-2030s. This rotorcraft lander will explore Titan's diverse surface, including dunes, plains, and possibly even lake shores, to study its chemistry and assess its potential for life. Dragonfly will build on Cassini's legacy by conducting in situ measurements, giving scientists their first direct look at Titan's surface conditions and complex organic chemistry. In addition to astrobiological interest, studying Titan deepens our understanding of planetary evolution. Titan's methane cycle may mirror early Earth's hydrological and atmospheric processes before the planet warmed and oxygen became dominant. By examining Titan's climate system and atmospheric dynamics, scientists can better model how planets and moons evolve over time, both in our solar system and around other stars. In conclusion, the discovery of methane lakes on Titan by the Cassini mission marked a monumental shift in planetary science. Titan, once a hazy enigma, is now recognized as a geologically and meteorologically active world with liquid on its surface, weather patterns, and a rich organic chemistry. These findings challenge the assumption that habitability requires Earth-like conditions and broaden the scope of where and how life might exist. Titan is not only a world of eerie beauty, but also a powerful reminder that even in the cold, dark corners of the solar system, nature finds ways to surprise and inspire. Saturn's moon Enceladus has a subsurface ocean 2005 to 2018. One of the most profound discoveries in planetary science came not from a planet, but from a tiny icy moon orbiting Saturn. Between 2005 and 2018, NASA's Cassini spacecraft transformed Enceladus from an obscure celestial body into a major focus in the search for extraterrestrial life. Cassini's flybys revealed that this small moon, only about 500 kilometers in diameter, harbors a global subsurface ocean beneath its frozen shell. Even more astonishing were the geyser-like plumes of water vapor, ice particles, and organic compounds erupting from its south pole, direct evidence of ongoing geological activity and a potentially habitable environment beneath the ice. Enceladus had long intrigued astronomers, but it was Cassini's multiple close encounters that revealed its true nature. The breakthrough came in 2005, when Cassini detected unexpected brightness near the moon's south pole and observed water-rich plumes shooting into space from fractures in the surface, features now known as tiger stripes. These jets were not only visible but measurable. Cassini's instruments flew through them, analyzing their composition in real time and sending back data that would change our understanding of habitability in the solar system. The plumes were found to contain water vapor, ice crystals, salts, silica, methane, carbon dioxide, and a variety of organic molecules, some of which are essential building blocks of life. The composition strongly indicated interaction between liquid water and rock, a critical clue suggesting hydrothermal activity beneath Enceladus's icy crust. Over time, Cassini's gravity measurements confirmed that these plumes were being fed by a global ocean of liquid water sandwiched between the icy surface and the moon's rocky core. This subsurface ocean is believed to be salty, stable, and in direct contact with the moon's interior, creating the essential ingredients for life: liquid water, energy, and organic chemistry. What makes this discovery so remarkable is that Enceladus is located far from the Sun, in the frigid outer solar system. Its surface temperature hovers around -200°C, too cold for liquid water to exist without an internal heat source. That heat likely comes from tidal forces, the gravitational interaction between Enceladus, Saturn, and neighboring moons, which flex the moon's interior, generating friction and heat. This tidal heating, concentrated especially at the South Pole, keeps the subsurface ocean from freezing and may drive the hydrothermal vents thought to exist on the ocean floor, similar to those found in Earth's deep oceans. These hydrothermal vents on Earth teem with life, fueled not by sunlight but by chemical energy. If similar conditions exist on Enceladus, it raises the tantalizing possibility that life could also exist there. Unlike Mars, where ancient signs of habitability are buried beneath billions of years of surface erosion, Enceladus offers an active system, one that is spewing its internal contents directly into space. This makes it uniquely accessible. Cassini was able to sample these plumes without even landing, and future missions could do the same, potentially detecting biosignatures, chemical indicators of life. The implications of this discovery ripple far beyond Enceladus itself. It has reshaped the criteria for where life might be found in the solar system and the broader universe. No longer are habitable zones limited to planets orbiting within a narrow range of distances from their stars. Instead, moons like Enceladus and Jupiter's Europa, which also has a subsurface ocean, show that internal heat and geological activity can maintain habitable environments even in the outer solar system. This realization has expanded the scope of astrobiology, prompting scientists to reimagine where and how life might arise. Cassini's mission ended in 2017 with a dramatic plunge into Saturn's atmosphere, a move designed to protect moons like Enceladus from contamination. However, the data it returned continue to fuel scientific discoveries and inspire future missions. One such proposal is NASA's Enceladus Orbilander, a concept mission that would orbit and eventually land on Enceladus to study its plumes, surface chemistry, and potential biosignatures in unprecedented detail. The mission could confirm the presence of life, or at least determine whether Enceladus is biologically active. In the meantime, the legacy of Cassini and the discovery of Enceladus' subsurface ocean continue to influence space science and public imagination. The idea that an ice-covered moon, so distant from the Sun, could harbor an ocean teeming with the ingredients for life is a powerful reminder of nature's complexity and unpredictability. Enceladus, once just another moon in the Saturnian system, is now considered one of the most promising locations to find life beyond Earth. In conclusion, the Cassini mission's revelation of a global subsurface ocean on Enceladus, complete with geysers venting into space, has fundamentally altered our understanding of what makes a world potentially habitable. Through careful observation and in situ analysis, scientists uncovered a geologically active environment that could, under the right conditions, support microbial life. Enceladus exemplifies how small, seemingly insignificant bodies in the solar system can become central to the most profound scientific questions, including whether we are alone in the universe. As exploration continues, Enceladus remains a bright, icy beacon in the quest to find life beyond our planet.